Good morning. Welcome to the very last lecture of the summer session on research methods. I have nothing to say but congratulations. You're almost there, right? So it's been a very intense 6 weeks, and judging from the assignments and the first two examinations, all of you have done a fantastic job. So I hope that you will be able to keep this up, right, for the last assignment, which will be posted very soon, and of course the final. Okay, hang in there. All right, so this is our last lecture, and today we'll be briefly talking about a very interesting test that is called the chi-square test. Um, so the reason that we should probably talk about it is because chi-square test is sort of um, a natural companion to what we discussed yesterday. So yesterday we talked about correlation, right? Or more precisely, we talked about Pearson product moment correlation. And well, first of all, right, correlation means simply the association between two or among more than two variables. That is, how one is associated with the other or other variables, right? So, previously we talked about, between two variables A and B, right? There's a possible positive correlation, right? As B increases, A also increases, right? And it is possible to have a negative correlation, that is, as one variable decreases, the other variable will increase, right? Um, or as one variable increases, the other variable will decrease, right? So it's going in opposite directions. And of course, right, we can have two variables that have no association, right? A flat line. That means you can have all kinds of change in one variable, right? This is one variable B, but the value of variable A stays constant. So there's no association, right? So we said that Pearson correlation is very good at establishing the association between two continuous variables, right? Continuous variables. That is, variables measured with interval or ratio scales: time, income, temperature, age, and in social scientific research, attitudes, right? Or other personality traits, how extroverted or introverted you are, right? So these are all examples of what we call continuous variables. So that's what Pearson correlation can do, establishing the correlation or association or relationship between two or more than two continuous variables. But we also sort of, briefly hinted yesterday that, it is not always the case that we have continuous variables, right? We could, for example, have two variables, right? Gender. So there's no way that gender is a continuous variable, right? However, we conceive gender as a concept. However, many, gender categories we come up with, right? It is gonna be categorical or discrete, right? So with men, with women, or we have other categories, right? Depending on what people do about this concept. And of course, we can have some other examples of categorical variables, right? So for example, we can have party affiliation, right? So at least in the US, we have several choices. We can have Democrats, we can have Republicans, we can have independents. Well, at least, right? Three sort of choices. So again, these are discrete categories. There are no sort of a continuation, right? amount of three. Rather, we say it's continuation. I think these two are really opposing each other on many matters, right? At least, in the US. But anyway, right? So these are examples of categorical or nominal, right? Nominal variables. That's just another way, right, of saying that these are categories. So what if you think that I try to associate gender with party, right? Um, then what do we do, right? So for example, right, you're trying to say, I want to examine whether gender is associated with party affiliation so that, women are more likely to be associated with, I don't know, I'm making things up, right? Republicans. Whereas men are more likely to associated with, are affiliated with Democrats. So if we plot this kind of conceptual relationship, right? So we have two gender categories. We have man, we have women, right? And then we have two, to make things simpler, two parties. We have Democrats, we have Republicans, right? So if we think there's a sort of a correlation between gender and party, and as we hypothesized, just for the sake of this, lecture, right? So women, which is said, are more likely to be Republicans, right? Whereas men are more likely to be Democrats. That means, sort of we can also draw a line like this, right? To link up these two data points. So that means, we can have men plot the data of men here, right? So we had a lot of men, right? It turns out that most of these men, they try to circle Democrats. Whereas we can also have many women, right? One, two, three, four. Many women choosing party affiliation. So surely there will be some women choosing Democrats, but there turns out, well, hypothetically speaking, right? More women are choosing Republicans. So if we look at this trend and sort of impose a sort of best fitting line, right? It will be something look like this. It's like a negative correlation, right? But of course that depends on how we position these two categories and how we position these two gender categories. But anyway, right? If we sort of configure our values, as these, it will be something like this. So in other words, it is possible to calculate a correlation, a trend, right? A trend that describes the association between two categorical variables. So this is one categorical variable. So these are two values of categorical variable that we call gender, right? And these are two values of a categorical variable that we call party affiliation, right? Sorry, party affiliation, right? So it is possible to calculate a correlation, but for many reasons we cannot actually, strictly speaking, cannot use Pearson product moment to calculate that. The correlation between two discrete variables, and in this context we need chi-square test. Okay, so this is the motivation behind learning this very useful technique. Okay, so it's, this is not chi or chi, but chi. So it's, if we use Greek letters, it will be something like an x, but not really an x, right? And it's squared. And we'll look at, why, it's squared, right? So this symbol will become, clearer at meaning in a minute. As we said, right, the purpose of this test or this statistical technique is to evaluate, to what extent the two nominal variables or categorical variables are related to each other. Okay, And of course, we should always keep in mind that, there's a, I should say, very big difference between these two tests at this level, right? So Pearson correlation is for two continuous variables, and the chi-square test is for establishing the correlation between two nominal variables. Okay, all right, just some basics. So let's be very concrete, and that will facilitate our understanding of this particular statistical technique. So let's say Andrew surveyed 980 people, right? On their gender, so simply ask them, what's your gender? And to keep things simple, right? I only use two categories. And Andrew also asked these 980 people what their party affiliation is. So they can choose Democrats, Independent, and Republicans. One and only one, um, you know, uh, answer to this question. Okay. So as we said, right, so these two are both nominal variables, and these are the values of this variable, these are the values of this variable. And the basic question that we could ask is there a correlation between gender and party affiliation such that one gender, or either gender, right, is more likely to be um, affiliated with a particular party, right? Either way, right? Doesn't matter. So it's said because these two, gender and party affiliation, right? These two are categorical variables. We can't use Pearson correlation. Instead, um, a chi-square test is needed. So to understand how chi-square tests work, we need to define some terms. Okay. So first of all, frequency. Actually, this is not a new concept. We have seen it before. So in the context of chi-square test, right, frequency measures or is a count of how many times, right, a particular category. For example, women, right, as a category, right? How many times women are observed in this sample? Or how many times Republicans, right, are observed in this sample? So how many times a category is observed? Or frequency here could also mean how many times a combination of two categories, like female categories or male Republicans or male Democrats, right? So this this one category is actually composed of two separate categories, and it's combination of two categories, right? So we can also count, how many times female Democrats are observed, or male Republicans or male Democrats and female Republicans are observed in our sample. Okay, so that's the first meaning, frequency. And then we need to distinguish between two types of frequencies. The first type is what we actually observe in the sample, right? We use FO here, right? Frequency observed. The second important frequency for the chi-square test is what we call expected frequency. So expected frequency, okay? And that is the frequency to be expected if the two variables, for example, gender and party affiliation, are actually not associated. Okay, let me repeat. Expected frequency is the frequency to observe categories or combinations of categories if the two variables, gender or party affiliation in our example, right, are not related. Okay? Well, very soon we'll be looking at the reasoning behind, establishing these two frequencies, right? Why we care about a frequency of observing the expected frequency, right, of observing something if the two variables under investigation actually have no association, right? Very soon we'll be talking about the reason behind this. The third thing that we need to remember or learn to understand the chi-square test is to understand a very basic mathematical rule that's called the multiplication rule. Okay, very simple. Let's start with something that we all should understand. That is to throw a fair dice, right? A dice, well, we should all know what a dice is, I think. A fair dice means this dice is perfectly made, such that there's an equal chance of getting a particular value, right, from 1 to 6, I believe, right, for any dice. That is the probability of throwing 1, 2, 3, 4, 5, and 6 are exactly the same, right? There's no bias towards any particular value on this dice. That will be a fair dice. Okay? Alright, so let me ask you then, what is the chance of observing 1 when you throw this dice, this fair dice, at the first throw? If you throw it once, what's the probability of getting a 1? Okay. And if you throw this dice again, right, you pick it up, right, you observe the first value that you observe, you pick it up and you throw it again. Then what's the chance or probability of observing 1 again, right, at a second throw? And we can also ask, what is the chance or probability, right, of observing 1 at both throws? That is, you should imagine you throw this dice twice. What's the chance of observing a 1 at a first throw and another 1 at a second throw? Okay, so this is the dice. And we should know, right? It's just, as if it's part of common sense that if this dice is fair, that is, it's not biased toward or against any value on this dice, then because there are 6 numbers, and imagine that when we throw it, we're not actually, be biased ourselves, right? So then chance of getting a 1 or any value indeed will be 1 over 6. And of course, if we keep throwing this fair dice, to get a 1 at a second throw will also be 1 over 6. And this probability will remain the same for getting a 1 and however many throws, right? It will always be 1 over 6. So that's the probability of fair dice. Okay, so given these two probabilities, that is, there's a chance of 1 over 6 getting a 1 at first throw, and there's a probability of getting a 1 at a second throw, right? 1 over 6 at a second throw. Then what is the probability or chance of you getting both ones, or 1 at both throws? So this is where the multiplication rule comes in. Multiplication rule simply says, right, if there are probabilities associated with two independent events, okay, there's one event, right, and there's a second event, and these two events are independent because the outcome you get from event 1 does not impact the outcome that you get from event 2. That is, you get a 1 at first throw, and getting 1 at first throw does not impact in any way which number you will get at a second throw. That is, or in other words, you cannot use the outcome from the first event or from the first trial to predict the outcome of the second event. right? If you can predict, right? Okay, so if I get a 1 at first throw, then I predict there's a chance that I'll get another 1 at a second throw, right? Then these two events are not independent, right? They're related, okay? But if you cannot actually predict, right? Well, here 1/6 was you say, well, Andrew, wait a minute. Didn't you say that there's 1/6 probability? Well, 1/6 probability simply means it's fair, right? There's simply you can't know, right, whether or not you will actually get a 1, right? This is probability, right? So what I'm saying here is you cannot use this probability to predict what the chance of observing um, this outcome, right? By knowing the outcome of this event. These two, throwing two dices, well, throwing a dice twice, right? These two events are completely unrelated. Okay? That's what we mean by two independent events, right? Um, are there some real life examples? I don't know. Totally independent events. Can you think of any? Well, off the top of my mind, I cannot think of a very ideal example that is as pure as this one because in real life, many things are not independent, right? I want to say the chance of you, well, how about this? The chance of you bumping into your classmates at two different days. I don't know, right? The 2 days might be related because of time schedule of the class. Well, anyway, right? I hope you understand this example here, right? These are two independent events. You cannot use the outcome of this event to predict the outcome of this event, right? For that, you will have two independent events. Okay, so the multiplication rule says if you have two independent events, then the chance of observing the same outcome at each event will be the product term of the probability of each event. So the probability of observing a 1 at a first throw will be 1 over 6, and the probability of observing another 1 at a second throw, which is totally independent of the first throw, is also 1 over 6. Then the chance of getting 1 at both throws, right? The joint probability will be 1 over 6 times 1 over 6. That will be 1 over 36. That makes sense, right? You can think of it. There are infinite number of, there's exactly 36 combinations for throwing two dices, right? There's 1, 1, 1, 2, 1, 3, 1, 4, 1, 6, right? So you can continue to emulate all the possibilities. Well, if you're not convinced, you can have 1, right? Imagine that the first time you throw 1, that's the first throw, right? The first throw you have 1. Then what's the possible outcome for the second throw, right? You have exactly 6 possible outcomes from 1 through 6. What if you have a 2 for the first throw? Again, you will have 6 possible outcomes, right? That's again what we mean by these two throws are independent, because by throwing any value, it is equally likely to get any outcome from the second event. It's not like if you throw a 1, it's more likely for you to get a 6 at a second event. If that's the case, these two throws will not be independent. But if you get a 1 at a first throw, but then the probability of getting a value at a second throw is totally random, right? Identical, right? It's equally likely for you to get a 1 as you will get a 6, right? That means the two events are independent. So if you get a 3 at the first throw, then again, it's equally likely to get 1, 2, 3, 4, 5, or 6 at a second throw. So there are 6 values at a first throw, right? That means, here you will have 6 possible combinations right? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 6 possible combinations. Here you will have another 6 combinations. Here you will have another 6 combinations. And because there's 6 outcomes first throw, then you will have 6 sixes. Well, if you have 6 sixes, that's exactly 36. Okay? And 1, 1, of course, is one of the 36 possible outcomes. So the chance of observing 2 ones, right, at both throws will be exactly 1 over 26. Okay, so that's another way to understand why a multiplication makes sense. Okay? All right. So, in general terms, right, that's exactly what we said. The probability, right, is using P to denote that. The probability of observing 2 independent events to occur at the same time, right? Observing 2 ones at 2 independent throws, right? Is the probability to observe event 1 to be multiplied by the probability to observe event 2, right? Probabilities of observing a 1 at the first throw of the dice times the probability to observe a 1 at a second throw, right, of the third dice, right? So let's change our sort of example to see whether or not we truly understand this. So in a sample, right, the frequency, or more precisely, relative frequency of observing women is zero point 0.5. That is, it's equally likely to observe a woman, to have a man, right? And slightly more likely we have more Republicans than Democrats. So 45% are Democrats. So frequency, right? So if the probability of observing women is zero point 0.5 and the probability of observing Democrats in the sample is 0.45, then what is the probability to observe female Democrats? Sound familiar? That's exactly the joint probability, right? If we assume, right, here's the key point. If we assume that being a woman is totally independent from being a Democrat, that is, if there are no association between being a woman and being a Democrat, then the probability of observing a female Democrat would exactly be, according to the multiplication rule, right? 0.5 times 0.45 equals to 0.225. That's the probability of observing a female Democrat if being a woman has nothing to do with being a Democrat. That is, you cannot predict a woman's party affiliation, right? You cannot predict a person's party affiliation by looking at the person's gender, right? You cannot. So that means gender and Democrats are independent, are unrelated, are not associated. So that's exactly how we calculated, expected frequency, right? So that's our expected frequency, or our expected probability to observe a combination of two categories if these two categories actually have no association, right? Independent. Okay? So now the total sample size, let me change the example a little bit, right? So now the total sample size is 980, and we have 577 women, and I have 444 Democrats. My question now is, how many female Democrats do you expect? So the keyword here is expect, right? So that means, or that suggests, you probably should consider calculating the expected frequency of female Democrats. And if you can calculate the expected frequency of, or expected probability of observing female Democrats, then you can simply use that probability to time or to multiply with this total sample size, and then you will have the number of female Democrats that you expect, right? So here we're talking about expectation, right? What you expect to happen if these two categories are not associated with each other. Okay? Okay, that should be easy, right? So first of all, we need to figure out, of course, from these numbers, right, what is the probability of observing women or females from the sample? That's easy. We have this many people and we have this many women, so the probability of observing women from this sample will be 557 divided by 980. Now would that make sense, right? And of course, like we can do the same to figure out the probability of observing Democrats from the sample. So, there are this many Democrats in the sample, and there are this many of people in total in the sample. So this is the probability of observing Democrats from the sample. Now, if we assume, right, because now we're sort of calculating expected frequency, that is, if we assume that gender and party affiliation are not related to each other, then what's the probability, right, of observing female Democrats? So in this case, if we assume that these two are not really related to each other, then we can use the multiplication rule, right, to time the probability to observe the first event, being a female, to time the probability of observing the second event, the Democrats. Okay, and then of course after calculating this, joint probability, we simply multiply this joint probability with the total sample size, and then that will give us the number of female Democrats that we expect. Okay? Right, this is exactly what, should happen, right? Number is 261.4 female Democrats that in theory should exist, right? So that's why we can have decimal points. This is the number that in theory should exist if there are no association between women and Democrats. And of course, this is our expected frequency, right? The count of the combination of two categories if these two categories are not related to each other. Okay? So that means, to interpret this number, if there's no association between being a man or woman and being Democrats, Republicans, or independents, right? There should be 261.4 female Democrats. I repeat, if there's no association, if gender and party affiliation are not systematically related to each other, that is, you cannot predict a person's party affiliation from that person's gender, then we can expect there will be 261.4 female Democrats in the sample. That's our expected frequency for female Democrats. So the logic or the core question that chi-square tests address is this, right? If we can calculate the expected frequency, and if we do have the observed frequency, well, this is what we observe, right? Is there any deviation of the observed frequency from the expected frequency, right? If the observed frequency is exactly or very close to the expected frequency, then indeed the two categories or variables are not associated, right? Because we can calculate the expected frequency based on the assumption that these two variables, x and y, right, they're not related to each other, right? There's no association between these two categories. And that's the assumption based on which we calculate the expected frequency. So now we have expected frequency and we also have observed frequency, right? So now we can compare these two values to see if the observed frequency is very similar to or very different from the expected frequency, right? So if the observed frequency is very close to the expected frequency, that means the assumption is correct, right? X and Y are not related. But if this observed frequency is very different from, or statistically different from, or meaningfully different from the expected frequency, that means this assumption is actually not correct, right? We cannot assume that x and y are related because the number that we observed is very different from the number that we calculate based on the assumption that these two are not related. That means this assumption is not attainable. Okay, so that's the core question that the chi-square test observes. Okay? Right, so the expected frequency is the frequency to observe a combination of categories, right, if the two variables are independent of each other. So that means, if the observed frequency is different from the expected frequency, then by rejecting, right, the assumption that the two variables are independent of each other, we'll begin to accept the alternative possibility that the two variables are actually related to each other, right? I repeat, if we observe a meaningful difference between the observed frequency and expected frequency, that means we're going to reject this assumption that the two variables are independent of each other. And by rejecting this assumption that the two variables are independent of each other, then the logical, alternative will be these two variables are actually dependent on each other. That means there is association, right, between these two variables. Okay, so that's the logic. And of course, if there's no meaningful or statistical, or meaningfully or statistically different difference between the observed and expected frequencies, then that means this assumption actually is pretty correct, right? Then the two variables we conclude have no association. Okay, so that's the logic of the chi-square test. Okay, so to compare and observe, to compare the so the chi-square test is all about comparing observed and expected frequencies, right? So now we need to sort of calculate all the observed and expected frequencies. To do that, we need to construct a contingency table, right? Actually, it's a table that we saw before, right? In this case, a 2 by 2. First categorical variable, which has two categories. We have a second categorical variable that also has two categories, right? So imagine this will be, imagine this is gender. So we have women, we have men, right? This is party affiliation, so that we have Democrats and we have Republicans, right? So for each cell, right, for Democratic women or female Democrats, we can have two values. FO, as we said before, that's the observed frequency. That's what we see from our data, right? We can count from our data how many, in this case, female Democrats there are. And of course, we just said we can actually calculate the expected number of women from the sample if gender and party affiliation are not related to each other. So we can also calculate, right, the expected frequency. So our task later on will be to compare, right, if this observed frequency is meaningfully different from the expected frequency. And we'll do the same for the remaining cells, right? We can easily observe how many male Democrats, right, there are in the sample, and we can calculate, well, within the sample, how many male Democrats we would expect if gender and party affiliation are not related. And then we can compare the difference, between these two frequencies, and we repeat the procedure for women Republicans and male Republicans. Okay. So now the question becomes, right, how do we, if these are knowns, right, in other words, FOs are known variables, right? because that's something we'll observe. So FOs are known and FEs are unknown, something we need to calculate. So then the chi-square test becomes a task of how to calculate expected frequencies, and we just looked at that. So to do that, let's return to our, party affiliation gender example. So here we have a 2 by 3 table, right? Because one variable has 2 categories and the other variable has 3 categories, so it's a 2 by 3. Now, we also know from our example that in total there are 980 people in the sample, so that's our sample size, n, okay? And by observation, we have these amounts of female Democrats, female independents, female Republicans, male Democrats, male independents, and male Republicans. So these are observed. So you can count from your data, or in examination, right? I'll give you these numbers. So these numbers in the black ink, right, will be provided for you. Okay. And then the question becomes, well, how do we use these numbers to calculate? So we have all the FOs, in other words, right? So we have N. We have total sample size. And then we have FOs here, right? That's first FO, second FO, third FO. We have all the FOs, right? Now the question is, let me use a different color. Now the question is, what are the expected frequencies? Right? What are the expected frequencies? Once we figure out the expected frequencies, we will have an idea, right? We can then compare the difference between, we can compare, how different observed frequencies are from expected frequencies. So my question now for you is, how do we calculate expected frequencies based on all these numbers? So recall, right? Previously, we said that in our previous example, right? The example that illustrates the multiplication rule is that if we have a proportion of females, that is, if we can figure out the proportion of females, say the proportion of female, as example, right, is 1/3, right? If that's the proportion or probability of observing females, and if we can figure out the probability of observing Democrats, let's say it's 2/5, all right? So that's the probability of observing females. That's the probability of observing Democrats, right? So if we can figure out these two ratios, then the rest is easy. We simply multiply them together according to the multiplication rule, right? Assuming that party affiliation and gender are not associated with each other. So then the question becomes, how do we get these numbers, ratios, from all these numbers here? Okay, you should think about it, right, before, pause here, and think about it before listening to my explanation, right? Okay, here's the idea. Very simple, actually, right? Let's start with figuring out the ratio or probability of observing women. So let me ask you, how many women are there in this sample? How many women there are in the sample? That's my question. Okay, so where are women in the sample, in the table? So we have female Democrats. So these are females. We also have female independents. These are females. We have female Republicans. So these are females. So are there any more females? No, the rest are males, right? So this column, or this row, sorry, this row represents males, and this row basically represents the females. So that means The total number of females in the sample will be to add these three numbers together, to sum them up. Interesting, right? We sum these numbers up. So 279 add to 37 added to 225, that will give us 577. That number can be used then to calculate the ratio, the probability of observing women, because we do have the sample size. Then it will be 577 divided by 980. That is the probability of observing women. Now you can ask, okay, so I get the idea, right? Then the question becomes, how do we calculate the probability of observing Democrats? Assuming that we want to figure out the expected frequency for female Democrats. Easy. Where are Democrats in this table? These are Democrats, and these are Democrats. So the total number of Democrats in the sample will be 279 plus 165. What is it? It will be 4, 4, and 4. So the ratio or probability of observing Democrats from the sample will be 444 divided by 980. There you go, you have the ratios. That will give you the multiplication rule, will give you the expected frequencies. And then we can do the same for men's, right? So these are men, these are men, these are men. So we have a total, by summing up these numbers, 403 men. How many independents? We sum up these two numbers. These are independents, these are independents. We have 120 independents, and we add these two numbers up, we have the number of Republicans, and we have 416 Republicans. Fantastic, right? So if we do the calculation, right, this product term will give us the probability, and we use this probability to time 980. That will give us 200, right? I'm right here. 261.4 female. So again, that will be our expected number of female Democrats in the sample if party affiliation and gender are not related. Similarly, we can calculate, right? Similarly, right, we can calculate how many female independents we expect from the sample if party affiliation and gender are not related. Okay, how do we calculate this? Okay, you should pause and do it yourself before listening to my solution, right? Okay, so let's do this together. How do we calculate the expected frequency here? Easy, right? So we know we want the ratio of female. Okay, let's change that. Let's calculate the expected frequency of male independence, right? So to leave women alone for a while. So how do we calculate the expected frequency for male independence? Easy. First of all, we need the probability of observing male. So we have these many males from these many people. So it would be 403 divided by 981. Fantastic. That's the probability of observing men, okay, from the sample, if gender and party affiliation are not related to each other. Then what's the probability of observing independents from the sample? These are the total amounts of independents from these many people. So you'll be 120 divided by 80. Okay, according to the multiplication rule. Okay, but then we want frequency counts, right? So we need to time or multiply this product term with total sample size. This will give you the expected frequency here. Okay, let's do this together. So first of all, you will notice that this 980 will cancel out this 980. Okay, that becomes these two being multiplied and then divided by sample size. Okay. Oh, excuse me. We can do this together. Okay. So it will be 403 times 120 divided by 980. Fantastic. If these two variables are not related to each other, then we expect, according to my calculation, 49.3 male independence in the sample. Pretty close, huh? We'll see. All right, so you can fill out the rest of the table, right? So for the final examination, you should be able to fill out the expected frequency, right? I'll give you these numbers, right? I'll give you these numbers. And you should be able to use these numbers to figure out the expected frequencies for all cells, okay? So you should use this as actually a chance of practice in addition to the assignments, right? Do the same. Okay, now we have everything. Now we have observed frequency, we have expected frequency, right? Observed frequency, expected frequency. Then a contrast, right? Then a contrast between expected frequency and observed frequency will be, of course, right? The difference between the observed frequency and expected frequency squared, that's why it's called chi-squared, and divided by expected frequency. Okay, so don't ask me why this is like this. Well, this will be beyond the scope of this class, but just just to know that this is how we calculate actually the contrast. Okay, and this will be for each cell, right? For each cell, we can calculate a contrast value. For this cell, we can similarly calculate a second contrast value and a contrast value for each cell. And then for chi-square, it will be the sum, right? The sum of all contrast values, right? And you will have the chi-square statistics. And this chi-square statistics will help you decide whether or not, right, there are enough difference between the observed frequency and expected frequency for us to reject the assumption that the two variables are unrelated, such that we can start to accept the alternative possibility that the two variables are actually related to each other. Okay? All right, so this is not required, all right, for the examination. You will not be required to hand calculate chi-square, but you are indeed required to be able to calculate expected frequencies. Okay, so this is not required, but this is required, right? How to calculate this guy here, given these values, given this value, given this value, this value, this value, this value, and this value, you should know how to calculate the numbers in blue. Okay, I think that's fair enough. All right, that will actually be almost the end of our class. Two things. First of all, e-cafe, right? Please spend a few minutes, really it's a few minutes, because it only has 10 questions, right? Please spend a few minutes answering the teaching eval at eCafe, so that I know what I can do to improve this class and what I can do to be a better teacher. Okay. I don't know. Shall I give you extra credit? I probably should, huh? Um, how many points do you want for completing the e-cafe? So we only have 5 people, right? So because really it's only 5 people, I do expect 100% response rate. That is, all 5 of you are expected to complete e-cafe, and if there's 100% response rate, each one of you will gain 5 extra points. How about that? 5 extra credits added to your score. How about that? But the requirement is 100% response rate e-cafe before it expires. Okay. What's the second business? Homework assignment 6, right, will be posted to Lalima very soon, likely within today, and there will be a study guide. Okay. And final exam will be on Friday at 10:30, George Hall. What is it? George Hall 213. Okay. All right. Thank you very much, everyone. Again, I don't have much, opportunity to meet up with you individually, because it's online class and because some of you are actually not physically here, understandably. But I expect that you have learned something from me from this class during the summer, so that it actually will be a fruitful 6 weeks for you. Okay, let's not be sad. I will see you around, and study hard, right, for the final. Okay, let me know if you have any questions, and this will conclude our content part for ComG 302. See you guys.